Hi, and welcome to Concept Based. I'm John Hepworth, and this is a Year 11 extension topic that was done actually earlier in the scope and sequence, but I wanted to go back and revisit it just because there are two different ways that this question can be done. And I've actually been on the side of the way of doing these questions that's probably a little inefficient. And having a look at the way that some people are solving these types of questions has made me want to change the method by which I solve it, which actually would be the second time that I've changed the method that I've solved these questions. Initially, when I was at school and when I started teaching this content, I just used to multiply by the denominators in these inequalities and then sort out cases of whether that multiplication was a positive or a negative, and therefore whether I should change the inequality sign or not, giving a particular domain range. But then, I know I was introduced to the idea of multiplying by the bases squared, therefore they were always positive and I didn't need to change the inequality at all. And I adopted that method. However, there's a little twist to this method. Well, not even a little twist. There's actually a change to this method that you can use. And I want to demonstrate today not just that method. I want to demonstrate what I've been doing as well, because what I want to show to you is possibly a massive change in the way that you might be doing it. Often with mathematics, the students that perform highest and most well are actually doing it because they're using really efficient techniques. So if you use a really inefficient technique, the chances of making an error are significantly increased and even getting lost sometimes. Whereas if you use the really efficient technique, then the chances of errors are significantly reduced and you can find your way through to the answer. So I'll show you these two methods, and I think the way that I've been using this, square the base method in this situation is definitely not efficient and can easily create problems and errors when you're doing the algebra involved. Then I'll show the other method. Now, something that I do want to just, point out before I get there at the end is that they're a little bit different at the end. You really do need to consider what's going on at the end in different ways. One of them's far more a testing points scenario, whereas the other one you can sort of use a graphical understanding scenario. So let me go ahead and show you these two methods. So first of all, I'll show you the method that I have been using for the last 15 years, this multiplying by the square of the base methods. So we'll multiply both sides by x squared, and we're going to multiply both sides by x minus 2 squared. So what we're going to get, on the left-hand side, we're going to have one of the x's is going to cancel, so we're just going to have an x multiplying up the top, because the denominator is cancelling with the x squared. And then we're also going to get that x minus 2 squared coming across from the other side is greater than or equal to, on the other side, one of the x minus 2's cancel, so we have x minus 2. We still have the x that's on top of this one, and then we're going to be multiplying by the x squared that's coming across from the other side. Okay, so now what I would normally do is I would normally tidy this up and move them all to one side so I could factorize them. So I will tidy this up. I'll have x outside of x plus 1, x minus 2 squared minus x cubed is coming across, x minus 2 is greater than or equal to 0. So now having done that, I can factor out the x minus 2 and one of the x's. So I'll go ahead and do that, x outside of x minus 2. And now when I create big brackets, I like to make them square just to differentiate them from the small brackets that I'm factorizing from. So on this side here, we've got an x plus 1 left and one of the x minus 2's. And then in this one, we've got an x squared left and no x minus 2 is greater than or equal to 0. Okay, so now I am going to tidy up the inside of those square brackets. And I'm going to do that by expanding. So we get x squared minus 2x plus x is minus x, and minus 2, and minus x squared is still there. And so now inside that bracket, inside that square bracket, we've got x squared minus x squared. Excuse me. And so we end up with x minus 2. I'm now changing back to curly brackets. It's minus x minus 2, but I never like to leave a factor in there with just a negative like that. So I'll take that negative out the front and have it as negative x, x minus 2, x plus 2 is greater than or equal to 0. Excuse me. So now that I've done that, what I would typically do is I would graph this. Now, please take into consideration here that this is negative out the front. So it's a negative cubic. We did talk about solving cubic inequalities back a few YouTube videos ago, if you want to go scrolling through the Year 11 extension content that I've created. And so I will now put in a positive 2, a negative 2, a 0. I will have a negative cubic. So it's going to go like this, and like this. And we want the sections where it's greater than or equal to 0. And so the greater than or equal to 0 parts, one of them's here and one of them's here. So for x, we will be less than negative 2. Now I'll write less than or equal to for the moment. And 0 is less than x is less than or equal to 2. Now we should go back in the top here and realize straight away that x cannot equal 0 and x cannot equal 2, because it would make the inequalities have 0 in the denominator, and we know that that breaks mathematics, so we don't do that. So 0 and 2 is excluded. So therefore, we will take the equal to's away from those ones, and the 0 and 2 therefore are excluded. And so we've got our domain where we have solutions based on a graphical method. Okay, so that's the method that I've been using for 15 years. It requires a little bit of graphing skill at the end to make it, I think, quick. You can go and test points, just like I'm going to do in this other method that I show you. The algebra looks like that. Excuse me. And the algebra looks like that. So it's, I don't know, it's not too bad, but it's not great either. So now I'll show you another way of doing this. And this other way of doing this essentially takes in the same sort of idea as what I'm doing, except one thing that it does is it doesn't subtract everything across to factorize. It just subtracts everything across straight away, so that when we're dealing with the fractions, we're dealing essentially with one side of the inequality, so we don't have to worry about it being positive or negative. I'll show you what I mean. So here we have x plus 1 over x minus x over x minus 2 straight away. So that takes away the need to multiply by the bases squared, because now we're just going to go and put the fractions together on one side of the inequality. We're not timesing both sides of the inequality by anything. So we can just go ahead and get x plus 1, x minus 2, minus x squared over x outside of x minus 2 is greater than or equal to 0. Then we can expand that top and get x squared minus x minus 2 minus x squared all over x. You can see there's some calculations here that are the same as the other method, but you can also see that it's significantly smaller. There's a lot less effort that needs to be made to get this into this factored form and ready to go for solving. So this is the other method, and this is what this algebra looks like. So you can compare the two pages. I think you'll find that this is definitely quicker. But I can't graph, well, I could graph this. Actually, could I graph this? I don't know if I could actually graph that straight off the top of my head. What I do know is that I don't have to graph it. What I have to do is take into consideration important points. When you have a polynomial and it's in a factored form, you just look at each factor, you know, the null factor theorem, and find the 0 points. When you're in a situation where you have a fraction like this, what the best thing to look for is points of interest, when things change. So what I mean by when things change, well, if you look at the numerator there, it's x plus 2. So at the point negative 2, the numerator will switch from being a negative into being a positive. In the denominator there's an x that's a 0, and also here a 2 would make a 0. Now, by having it in this form, it actually points out to you straight away, x can't equal 0 and x can't equal 2 in the solution. You don't have to go back up the top and remember whether those things were included or not, because you can just see that they're not included in this part of the question. So now we've got these regions between these. We've essentially got 4 regions. And what we could do is go and chuck values in and see whether we end up with it being positive or negative in these regions. And therefore we can go ahead and include them or exclude them. I'm not going to do that because I already did the graph earlier. So I know that this section ends up being positive. This section ends up being negative. This section is positive and this section is negative. And we want it to be positive because we want it to be greater than 0. So therefore, with that being the case, we will go and accept this section, which we know is x is less than or equal to -2. And then in this 0 section, as we know, it is not equal to, because 0 and 2 are excluded. So there you go. There's the 2 methods. Here's the new method that I'm using after 15 years of doing the squared of the base. I would even love to show you the method I was using in my first few years of teaching, where I was doing it as a case base. When x is greater than 2, when x is less than 0, if this and all of that. Definitely more complex, definitely confused a whole bunch of kids doing it that way. So I was happy with the square denominators. But yeah, I think this way is definitely better when it's dealing with inequalities with fractions in them and unknowns in the base. If we were to go back to like an extremely easy example, something like 5 over x plus 1 is greater than or equal to 2. I'd probably still just multiply by the square of the base in this one. I'd probably still stick with it just because I've always used this method. And so I'd probably just do that in this situation. But if there's something where it's got, different things, unknowns in the denominator on both sides, I think then, I probably will go and use this new method, because when I say new method, there's nothing new about it. I will use this method because I think it's just going to end up being a little bit easier. So yeah, as you can see, there's not much working involved when I use my old method and I do this sort of a one. I just end up in a quadratic, which I have to then go and solve, and I would get an answer. Whereas if it's if it's the new method and it was an example like this where the denominator isn't complex, then you end up with one that looks like this, and you don't have to use a quadratic formula. So it still definitely has value, to just go and look at these points. 5 minus 2 is -3, so minus 2x minus 3, plus 3. 5 minus 2 is 3 over x plus 1. Yeah, see, I avoid the quadratic formula even in the simple case. So look, choice is yours. I probably just need to accept that moving these fractions across to one side is just the better way to go. And I will try and do that from now on in the future.